Hi folks, and welcome to tonight's live session on rational functions, and with a small segment there on inverses of radicals. So if you have any questions, as always, there's a chat box over on the right hand side. Please post those questions right there and I'll be happy to answer them along the way. So without further ado, let's get started. So with rational functions, we're going to begin with the domain because that's the main part you need to start with. You need to know what numbers you can plug in. So in this case, how do you determine that? Well, think about it. In terms of the domain of a function, those are the values that we are allowed to use. So we can actually look at the values that we can't end up using. And so, for example, what we'd be doing here is if you have a 0 in the denominator, you have a problem. So we're going to try and solve that by setting the denominator equal to 0 and then figure out all the values it can't be. So actually, I'll write out for the first step, we have that this denominator cannot equal 0. And so in order to solve it, I'm going to actually do just the opposite. I'll set it equal to 0 and find all those values that would allow it to equal 0. So I know this seems kind of confusing at first, but you'll get the hang of it real quick. So notice in this polynomial, we have x appearing right there as a factor of each term. Oh, actually, I'll write it this way first. So we have x, and then after you factor out that x squared, you have an x squared minus 5x minus 14 equals 0. And then you'd get x, and then you'd have the quantity here. We can actually factor that nicely. So we have x is in both terms. You're looking for two terms that multiply to negative 14 and add up to negative 5. Well, notice if you do a negative 7 and a positive 2, you get negative 14 as the multiplication, and negative 5 is the addition. So that satisfies our conditions there. So in order to do this, we'd have x equals 0, x minus 7 equals 0, and x plus 2 equal to 0. So moving forward from there, what do we get? Well, we get x equals 0, we already had. We have x equals 7, and x equals negative 2. So what we have, if that would be where it equals 0. If we don't want it to equal 0, that means x cannot equal. So our choices are 0, 7, and negative 2. And if you're to draw this on a number line, not saying you have to, but just in case it does help people, you put negative 2 here, you put 0 right there, and then 7 a little bit further on down the road. We have open circles at those spots because they are not included. So if you're drawing out, you have shaded regions in between those open circles. Those are all values that are allowed. And so we're going to have, if you notice, should have 4 intervals. Now how do we connect intervals? Well, we end up using a union symbol. Okay? So with that in mind, what do we have? Well, we start from negative infinity, that's the furthest to the left, and we go all the way to negative 2. We do not want to include negative 2, so we put a parentheses. Then we put a union symbol to get the next interval, which would correspond to this from negative 2 to 0. And we don't want to include 0 either, so we just put a parentheses. And then we go from 0 to 7, which we don't want to include 7, so we put a parentheses. And then we go from 7 to infinity. So if you have it in interval notation, that would be your final answer. Now what's more, we're actually going to learn here in just a second, is the scenarios of what type of discontinuity we have in the denominator. So since it's not a domain, in our domain, we're going to have a discontinuity there. And so what type do we have? Well, that remains to be seen, but you'll involve the numerator just a little bit, and you'll actually see that in this case, all of those values would actually be vertical asymptotes in this graph. So if you're wondering about that, that's what's going to happen. So in terms of the discontinuities, that's what I just mentioned, there's 2 main types that we're going to discuss in this section. There's actually a third type if you talk about piecewise functions, and that would be a jump discontinuity. But so there's the infinite discontinuity. And then there's a removable discontinuity. So from the infinite standpoint, if you have a graph And what happens at an infinite discontinuity, you're having some form of a vertical asymptote. And so it's called an infinite discontinuity because at least on one of the sides you're going to have it approaching either positive infinity or negative infinity, or both of them approach positive infinity, or both of them approach negative infinity. So that's what happens in an infinite discontinuity case. In a removable discontinuity case, you have a graph that goes along pretty smoothly. It could have an infinite discontinuity as well, but so that would be a removable discontinuity. It's called a hole, right? So these examples here will have cases of both, and I'll kind of explain what to start looking for. The first thing, though, that you should always do if you're seeing what type of discontinuity is to factor completely what you have for your rational function. So I'm going to do that, and we're going to discuss what happens. So in our first case, notice you can factor out an x pretty easily in the numerator, so you're left with x squared minus x minus 2. And in the denominator, you can also factor out an x. And then you're left with, oh, actually you can factor out a 4x, to be honest with you. That'll make our life a little bit easier. And then we're left with just an x plus 1. So this whole thing equals, well, we have x, and then how can we factor the numerator? Well, x minus 2, or you have an x and you finish with the minus 2, so we're looking for two things that multiply to negative 2 and add to negative 1. So that means you're going to have a negative 2 and a plus 1. So notice, though, that this thing, you get 4x, and then you have that x plus 1 sitting right there. So what happens? First off, our domain, hopefully you can see you set the denominator equal to 0. Yeah, so negative 2 and plus 1, that's exactly right. You got it right on the money there. So in this case, when we look 4x times the quantity x plus 1, what happens? Well, our domain, we have x cannot equal whatever would make the denominator 0, and so that's going to be 0 and negative 1. So those are going to be your discontinuities. Okay, if you need to see how we came up with that, just let me know and I'll be happy to show you. But in terms of those being our discontinuities, now we have to figure out, well, what happens at those discontinuities. And so here's the whole idea. Notice that the degree, or I shouldn't say degree, the multiplicity, if you remember what that is, the multiplicity of the x equals 0 being in the denominator, that multiplicity is 1. And the same thing happens up above. And let me actually make a different color here. So with the blue, what's going to happen is that those two things cancel out. And so since they cancel out, what you actually have is a removable discontinuity. At x equals 0. Now, I should kind of give you a warning. Say you had an x to the first in the numerator, and you had an x squared in the denominator. Notice both of those are giving us x equals 0. It won't work. But since the square, the multiplicity of the denominator, is actually larger than the multiplicity of the numerator, that would actually turn into an infinite discontinuity. So that's the tricky case in terms of what you could run into. But just kind of keep that in mind in terms of what happens. Since these things canceled out, everything worked hunky-dory, and we didn't have to worry about the denominator. So I'll actually simplify this at the end of what this thing's going to look like. Oops, sorry about that. Let's see if I can get that hooked back up. There we go. Alright, so our removable discontinuity at x equals 0, hopefully that makes sense. Just beware if you had, also on the other end of the spectrum, if you had an x squared in the numerator, so meaning multiplicity of 2 or higher, and the multiplicity of the denominator stayed at 1, then that would still remain a removable discontinuity. So the only case where it changes to an infinite is if your denominator has a higher multiplicity than the numerator for that root, essentially, of what the polynomial is in the denominator. Now in our second case, notice actually we have x plus 1 appearing in both the numerator and denominator, so that cancels out. So what that means, notice both of them have the same multiplicity. Once again, we get a removable discontinuity. So you get removable discontinuity at x equals 0 and at x equals negative 1. Now let me explain what's happening here a little bit more for the bigger picture. Notice this thing simplifies to, well, you have the 1 over 4 essentially times x minus 2. So in terms of the graph, what can we get? Well, so if we had this thing graphed, notice when you plug in 0, you'll get negative 1/2. And let me draw the graph in red, say. So 0, if you plug in, so I should put 2 extra comments. X cannot equal 0 or negative 1. With this, at 0, negative 1/2, for when we plug that in, we're going to get a hole. In a similar manner, when you plug in negative 1, you're going to get negative 3/4. So you're going to get another hole at negative 1. Negative 3/4. Oops. I know it's hard to draw here in the tiny space. And then notice that thing equals 0 when x equals 2. So we'll get something that looks kind of like this. Pretend, don't let your eyes fool you, that's a straight line. So the coordinates of that point, well, that should be a different color. So I'm just trying to indicate this point right here will be the point negative 1, negative 3/4. That's where one of your holes is. And the second point, that would be 0, negative 1/2, just by plugging it into that new equation. And that's all that's happening at a removable discontinuity. Once you simplify, you can plug it into the new equation, and that's where your hole will occur. If you have to go on to calculus, it's a big concept that you talk about in limits, as a matter of fact. And so you'll try and figure out what that y value is all the time. But you actually can do it from pre-calculus. So hopefully that makes sense on that one. Let's try another, just to try and make sure we can hit this home. So we have g of x equals 3x squared minus 75. So in order to do this, we better try and simplify this a little bit. Notice you can factor out a 3 in the numerator. That becomes x squared minus 25. And then the denominator, what do we have? We have x cubed. So this would be, we can factor out an x, so we're left with x squared minus 6x plus 5. So that tells us something else now. So we can factor the numerator. You get 3 times x minus 5, x plus 5. Okay, and in the denominator you get x, and then we need to look for two factors that multiply to 5 and add to negative 6. Well, we don't have many options. It's going to be negative 5 and negative 1. So notice now our domain, once again, is x cannot equal, so we can't have 0 from the first factor, you can't have 5 for the second factor in the denominator, and you can't have 1 in the third factor. Now what we need to do is check the numerator as well. Okay, so let's see, does anything cancel out here? Well, notice you have an x minus 5 in the denominator and an x minus 5 in the numerator. So, and they're both the same multiplicity. Once again, that's important. So that means we have a removable discontinuity at x equals 5. Yeah, very good. So I see the x minus 5 popping up for what the factor was. That's awesome. Getting that down. And then, so now, notice the other two, though, they don't appear in the numerator. So with that in mind, what does that mean for that type of discontinuity? Well, in that case, you're looking for an infinite discontinuity, because there's nothing in the numerator to cancel it out. So you'll actually have that asymptote hanging out right there. So infinite discontinuity at x equals 0 and also x equals 1. And that's pretty much all this was asking for right now. And hopefully that makes sense on that bit. Okay. If not, let me know. I'm happy to clear that up a little bit more. But always look for you're looking for the roots of the denominator essentially, and seeing if any of them line up with the numerator. That's how you can tell if it's a removable discontinuity, if they have the same multiplicity, or if the multiplicity of the numerator is higher than the denominator. That means you're having a removable discontinuity. Otherwise, it's an infinite discontinuity. Okay, if you have that denominator being equal to 0. Okay, so moving forward, where do we go from here? We've seen the discontinuities. We can start talking about M behavior. Okay, so now here's a more general sort of idea as to what happens. In terms of what we're looking at, so if we have f of x be this general polynomial, now I know we see n's and m's and all that, it looks scary, but there's three scenarios. So scenario 1. If n equals m, then there exists a horizontal asymptote Now, horizontal asymptotes are the y value. And so this is going to be at y equals. So if n equals m, that means this value and that value are the same. So what we do, x is your variable, so that means that a sub n, and then the b sub m are your coefficients. And so what you'll have is a horizontal asymptote at y equals a sub n over b sub m. In other words, what does that mean? That means as x goes to infinity, or negative infinity in this case, as x goes to infinity, y approaches a sub n over b sub m. Okay. Scenario 2. If n is greater than m. Oh, actually, let's do the other way around. We'll do m is greater than n is less than m. So that means the degree of the denominator is larger than the degree of the numerator. Then there exists a horizontal asymptote at y equals 0. So in other words, as x goes to infinity, or once again I can put in negative infinity, y goes to 0. So that means last but not least, scenario 3, if we have n being greater than m, then there does not exist a horizontal asymptote. And we're going to turn this into a scenario where we're just looking at a polynomial of a certain degree. So in the M behavior, resembles, so meaning it goes to positive infinity or negative infinity since you don't have a horizontal asymptote. So in that resembles, we have a sub n over b sub m, and then it'd be x to the n minus m. Okay, I could get a little more particular if you want to see things like slant asymptotes and things like that. You can divide, so that means there's a difference in the degree by 1. So basically n and m differ by 1 and n is greater than m. So meaning m equals m minus 1 essentially. In that case, you can divide the two polynomials and you can even get that constant to tell you exactly what it looks like. So if it's more, we're just looking for it approaching infinity or negative infinity, but if you're looking for more in terms of what's a slant asymptote or what sort of functions are we approaching in the long run, you can do polynomial division and figure that out as well. So the best thing, you see these three different scenarios, how the heck do we use them? And that's what I'm going to focus on here. So in terms of the first one, I'll switch colors here once again. We have to find the degree. All of it boils down to the degree. So notice we were talking about over there was the degree of the polynomial was n and m. It was easy because it's listed in order. Not always will these things be listed in order. So first off, look at our two degrees. You have 7 and 5. So degree of the numerator equals 7, and the degree of the denominator equals 5. So if you refer back, I'll go back real quick so we can take a look. What do we see? Which scenario are we dealing with? Well, notice your degree of your numerator was 7, your degree of your denominator was 5, so that means we're dealing with scenario 3. So right out the gate, we're going to have either positive infinity or negative infinity. So what does it say then? It says look at the coefficients in front. So if we look at the coefficients in front, what do we get? Well, your coefficient in front of the numerator is 5. Your coefficient in front of the denominator is, now this is where people trip up as well, you have a negative 9. So the behavior of this will be the same as just if we look at 5 over negative 9 and then x to the 7 minus 5. So what does that approach? Well, this thing approaches negative 5/9, so we have a negative number, and then x squared. Well, wait a second, x squared and we multiply by some negative, that means we get something that looks like this. Now, I'm not saying the graph overall of f of x approaches this graph, but the end behavior is the main thing. So if we kind of focus on these two parts, so you're going to get an end behavior like this and another end behavior like that. Okay? So the middle stuff is what's up for grabs in terms of how this thing is arranged. So now what that tells us is, as for end behavior, as x approaches positive infinity, the y value approaches negative infinity, just from that. And then as x approaches, once again we have negative infinity, we still have that y approaching negative infinity. And that's it. You're done. Right? It only takes a couple seconds. These are actually, end behavior freaks people out, but it's really quick and hopefully easy for most of you. So on our next one, notice you have a pi x to the first power minus ex to the fourth. So your degree of your numerator is 4. Your degree of your denominator is 7. So notice, and I'll write that out, degree of the numerator equals 4, and the degree of the denominator equals 7. So this time the denominator wins. So I'll go back so we can take a look in our notes. Oh, okay, so we're talking about scenario 2. So notice that means we have a horizontal asymptote at y equals 0. So I'll write that down. Horizontal asymptote at, remember it's always y, not the x, at y equals 0. So in terms of what does that mean? Well, that means as x goes to infinity, y goes to 0, and as x goes to negative infinity, y goes to 0 as well. Just an FYI, there will be functions out there later on down the road where you will have things approach x going to infinity, approach one horizontal asymptote, and then y, as x goes to negative infinity, your y value will approach another horizontal asymptote. That can happen. Or it might not even approach a horizontal asymptote on the other end at all. When you get to exponential functions, you'll see that as well. So just beware, you could have other scenarios pop up. Okay, oh, and let me know, is the shorthand making sense? If not, please just give me a heads up and I'll be happy to write things out a little bit more thoroughly, but hopefully this gets the gist of what's going on. Notice the last one, we didn't even have to check the coefficients in front, so that's the beauty of when you have one less than the other. Don't even have to worry about the coefficients. The denominator, I should say, being greater than the numerator for the degree there. That's when we don't have to check. In our third scenario, though, notice we have 3 up here and 3 down below. So in our case, our degree of our numerator equals the degree of our denominator. And that's the first scenario. So what do? Well, we check the coefficients in front of that degree, that term with the degree. And so here's what it tells us. Well, we have a horizontal asymptote. At y equals, well, you just take the coefficient there for the numerator, you write that, and then you divide by the coefficient for the denominator, and you're done. Simple as that. So in this case, what we have is, if you were to write this out, as x goes to infinity, y goes to negative 7/19. Oh, great, we got a question here, so let me read it. So the definition of x going to infinity is just defining what the graph is doing at the end behavior. Yeah, that's exactly right. It's just saying this as x goes to infinity is just discussing exactly what the end behavior is. If you actually go on to, I keep on bringing up calculus, you'll see this symbol. So here's how we kind of shorthand this. If I call this g of x, so the previous one, what we say is we say the limit as x goes to infinity of g of x equals 0. Whereas in this case, we have the h of x, we'd say the limit as x goes to infinity of h of x equals negative 7/19. So for those of you that like using Google and stuff, if you see this this LIM and then you have an X with an arrow, it's just the same notation that I'm using here. We just toss some different words. It's just like learning a new language. That's all math really is. So we're just kind of getting the lingo down in terms of end behavior. Oh, horizontal asymptotes is a fancy name for talking about the end behavior because it's approaching a number. That's all there is to it. So hopefully that makes sense. If not, let me know. I'll be happy to clarify a little bit more too. So finally, we have as x approaches negative infinity. Oops, there we go. We have y approaching negative 7/19. And so if I were to write that out with this lim symbol, lim as x approaches negative infinity of h of x, that also equals negative 7/19. So you don't have to know that last notation where you see the LIM business, but I just want you to, if you do go on, you can see here's what's happening, and that's how all those problems work out. Okay. So the next bit, determine the intercepts of the following rational functions. There's technically two parts that we got to kind of check out when it comes down to this. I'm actually going to ask a question first. How do we determine a y-intercept? So I want to see what you all remember. And then also, how do we determine an x-intercept? You can tell me, and then hopefully we can kind of move forward from there. And in the meantime, I'm going to factor the denominator here real quick. Yeah, so the y-intercept is very good, Catherine. So, and Catherine, you can email me. You get a bonus point for that. So if you let x equal to 0, you get your y-intercept. And yeah, so like f of 0, that's exactly right. And that's exactly what you do all the time. So the y-intercept business, that's usually the easy part. But I'm going to give one little notion that we have to watch out for from time to time. In this case, it won't come into play. But so for y-intercept, what we'll check, that's the easiest part. And you go f of 0. So that's exactly right. And so Josh, you get another bonus point there. You can shoot me an email. You get when the numerator equals 0, the same song and dance, that'll give you the x-intercept. So those are the two intercept parts. And so just both of you, Catherine and Josh, shoot me an email. I'll be happy to give you extra credit for that too. So yeah, moving forward on this thing, what happens? So notice we need two numbers that multiply to -3 and then add up to -2. So you get x, and then we want -3 and then a +1, and that gives us that sort of scenario. The numerator might be a little bit trickier, and right now, as soon as I saw that, that actually tells me something as well. It tells me the domain, and this is why I held off from doing the f of 0 business first. So the domain now, what we can say is x cannot equal -1 or +3. So what that tells us is that 0 is defined. You can run into a scenario where it's not, and then we don't have a y-intercept. We could have a removable discontinuity or an infinite discontinuity when x equals 0. So in this case, we can find the y-intercept right away. So, but just a heads up, you might run into trouble every now and then where it's undefined at that point. And you can just plug it in and see. If you run into a problem where you're dividing by 0, you know right away that's not going to work. So in this case, though, we get 0 cubed plus 2 times 0 squared and minus 9 times 0 and then minus 18. And really, I don't need to plug it in. There's an easy way to do this. You just look at the constant terms if it's possible. And in that case, we get negative 18 over negative 3. And that makes positive 6. So our y-intercept occurs at the point 0, 6. In terms of our x-intercepts, as Josh mentioned a second ago, he said, hey, if we just set the numerator equal to 0, we can find our x-intercepts. Yeah, and so in order to do that, though, I'm actually going to do something a little bit neater in terms of trying to factor that. You might not know how to factor a cubic. I'm not saying this will always work, but it's good practice for us. So minus 9x minus 18. There's this idea of grouping. So you can group the first two terms, oops, there, and then you can try and group the second two terms. But notice if I factor out the minus symbol, I have a plus here. Because a minus was distributed to both of those terms. Now, factor out an x squared in the first two, you get x plus 2. And then we can factor out a 9 in the second one, so you get 9, and then we get x plus 2. And so what that tells us is that this becomes x plus 2 times x squared minus 9. X squared minus 9 can factor as well, so we can rewrite this as x plus 2, x plus 3, x minus 3. So now, I like the idea a lot of setting the numerator equal to 0. But here's where we have to be careful. And hopefully the factoring made sense. If not, let me know. I'll keep it up there. But otherwise I'm going to erase it because I'm going to need that space there. So when we take this now, we have that factored version, because that's what we're always going to want to do. We can set the numerator equal to 0. But there's one problem with that. Notice this factor right here is going to cancel off with that factor right there. What we need to notice is that there's a removable discontinuity at x equals 3. That would have been a solution, but what happens, it's no longer a solution. Yeah, that's perfect. There's a removable discontinuity at x equals 3, so we have to watch out for that. That is not an x-intercept. That's a hole. So you're going to have a hole. It's actually going to be where the x-intercept will occur, but it's not included in our graph. It's just an open circle on our graph. So that's one bit that you're going to have to watch out for. Now, the other parts, though, they should work out nicely. So we set x plus 2 equal to 0. And then we let x plus 3 equal to 0. So notice we get x equals negative 2 and x equals negative 3. And so in this case, what happens? We have an x-intercept, and I should write intercepts, at, well, this will be negative 2, 0, and negative 3, 0. And that's our final answer. So we have all our intercepts involved. Okay? Hopefully that makes sense on those little bit trickier cases. I want you to be aware of how these things work and all that jazz. Alright, so in our next one, our domain of g of x, so let me go back to blue, I guess. So we have to find our domain, make sure we have no problem points. You just set the denominator equal to 0. You have x cannot equal negative 4, positive 20, and negative 2. Even though you see this square in the cube there, that's not going to make a difference whatsoever. So, in terms of what happens from here now, well, we have the domain, and now we need the y-intercept. This is actually going to be a bit of a pain. It's not going to be a pretty number. Remember, all I said, we have to watch out for the constants. So if you plug in g of 0, if you want to see me write 0 minus 5 the quantity squared and 0 plus 3 the quantity squared, so on and so forth, I can. But the main gist of what I'm trying to get at here is we're going to have negative 5 squared, 3 squared, then negative 6, and a positive 4. Because all the rest of those terms are zeros. And notice, reason why we can just plug in right away, we don't have 0 as not being in our domain. In the denominator, you have a 4, you have a negative 20, And then, oh, that negative 20 is actually cubed, so that's going to be fun. And then, what else do we have? We have a 2 squared. Okay, so let's simplify this thing a little bit. We get that 4 and that 4 cancel. What else can we cancel here? So we can rewrite negative 20 cubed. Well, actually, let's do this. So negative 20 can be rewritten. We can pull out the negative symbol, but that's going to be 5 cubed times 4 cubed. And then times, you'll have 2 squared. So now what happens is you'll have the negative 5 squared. Notice that just becomes a positive 5. So that'll cross off with 2 of those terms. And obviously you can use a calculator if need be. The 2 squared, that'll cross off with one of the negative 6's. It has a 2 involved, so you can write this as negative 3. And that'll cross off the square there. And so what do we have? So we'll have 3 squared times a negative 3. That makes negative 27. And then all over, okay, so what are we left with? 2 times 4 cubed. 4 cubed is, so 4 squared is 16. 4 cubed is 64. 64 times 2 is 128. So that will be, oh, and I need the negative symbol there. So negative divided by negative makes a positive, so that means our y-intercept occurs at 0, 27 over 128. Okay? So all that, as I said, you can use a calculator, no big deal there, and that'll do the trick as well. But hopefully that illustrates that component. Now for the x-intercept, we set the numerator equal to 0, but we got to watch out for other factors. So notice x plus 4 appears in both the numerator and denominator, so those things are gone. The 20 and negative 2, though, they don't. So really all we do is set x minus 5 squared equal to 0. But notice the square doesn't matter, so you just go x minus 5 equals 0. And then you have the x plus 3 equals 0. We aren't worried about discontinuities or anything like that in terms of what type. So that's why we can toss away the squares and things of that nature. So you get x equals 5, and then you get x equals negative 3, and then you get x equals 6. And so we have 3 x-intercepts, and they occur at 5, 0, negative 3, 0, and 6, 0. Okay, hopefully that makes sense on that. If not, let me know if there's questions. I don't see any at this point, so I'll keep on moving forward. So hopefully the intercepts, the discontinuities, and all that jazz kind of come together to make some sense. Because what we're going to try and do in the main piece is, if we want to create a graph, now there's ways to create the whole thing. I'm just going to focus on the main points where you can start to see, oh, if I look at this graph, here's what must happen. Okay, so list the main components of the graph. First things first, you got to list the domain. So notice we cannot have 0 in the denominator. That means x cannot equal 2, 3, or negative 2. So now we have discontinuity. So we can say the types of discontinuity. So if you notice, the x minus 3's have the same multiplicity, same degree, or same multiplicity in both the numerator and denominator. So that means we have a removable discontinuity at x equals 3. We can even find out that y value, and I'll do that in a second if need be. And then, so notice what that says to us is f of x is basically simplified to x minus 1, and then you have x minus 2, x plus 2. And so here's the simple way to figure out the y value. All you do is you plug it in, and so, oh, and I have x cannot equal 3 because it was once in the denominator. So the way to figure out the y value there, you get 3 minus 1, you just plug it into this, and then you get 3 minus 2 and 3 plus 2. whoops, 3 plus 2. And so your removable discontinuity, you get 2 over, this is 1 times 5, so 2/5. So what that means, just an FYI, that's a hole at 3, 2/5. Okay, so that means as well, since the others don't have anything in the numerator to worry about, they're infinite discontinuities. Discontinuity. And so those occur at x equals 2 and -2. Okay? So we have that so far. We can talk about the end behavior. Oh. Sorry, I got kicked offline there for a second. Hopefully I'm back on. Can you hear me now? Are we good to go? Okay. Looks like we're back rock and rolling. So in behavior, what must happen there? Well, in order to do that, you might want to expand the polynomial. You can expand either one, that'll do the trick. If you expanded the first one, you could rewrite this as x squared minus 4x plus 3. And in the second case, notice you would get an x cubed. And so what would we get? There's a negative 2x squared. Well, let's do this. Go x squared minus 4 times x minus 3. That'll be a lot easier. So we'll get a negative 3x squared. And then we'll have negative 4x. And then plus 12. And notice actually I didn't even have to go that far. All I needed was those first couple terms. And so if you look, we have the square and the cube. Degree of the denominator is larger, so that means we have a horizontal asymptote at y equals 0. Okay? And then last things we're going to need are the y-intercepts and the x-intercepts. Yeah, so it's going to be y equals 0 is what we're kind of looking at, and then we're going to plug in, for the y-intercepts, we're going to plug in 0 in for the x. So you get y-intercepts goes to f of 0, which equals, you can actually use the simplified formula because 0 minus 3 divided by 0 minus 3 are going to cancel anyway, so I'll actually use that in this case. So we'll go 0 minus 1, and then you get 0 minus 2, 0 plus 2, which equals negative 1 over negative 4, which equals 1/4. Okay, and then that means the x-intercepts, and so that means 0, 1/4 is your y-intercept, and then your x-intercept would be given by just when the numerator equals 0. We'll notice x minus 3 is out because it's a hole, it's a removable discontinuity. So that means we're just looking when x minus 1 equals 0. So that implies that x equals 1, or the point 1, 0. So you're going to have a whole cluster of points at the end of the day kind of near each other. But to kind of give an illustration here, so you have a graph. Okay, what's this thing going to look like? Well, some of the points you can put on there. You have a solid dot there at 0, 1, 0. You have another solid dot at 0, 1/4. Don't let your eyes fool you. That's supposed to be 1/4, where that other black dot is. So now what else do we have? We have 3, and then 2/5 is a hole. So if I move over to the 3, I got to be 2/5, so that'll be what? Get that common 4. That's 8 over 20 versus 5 over 20. That'll be slightly higher. So I'm going to draw an open circle slightly higher. That's supposed to be below 1/2, but higher than that 1/4 mark. And then what else do we have for our infinite discontinuities? We have x equals 2, so I'm going to draw a dotted line, meaning some form of an asymptote here. And then at -2, I'm going to do the same thing. So now, moving forward from here, you can kind of start to figure out what the graph's like. So you know that if you go beyond -2, you can plug it in, by the way. If you plug in, say, -5 into our final equation, so when you plug in -5, notice you get a negative on top, get a negative here and a negative there. That means the overall thing is negative. So that's telling you, since you're going to 0, you're going to be going from this side. And you might be saying, why do I know it's that side, and why can't I cross the graph here? The graph might be slightly off in terms of concavity, but the most part of that's the gist. The reason why we know that the graph has to be below the x-axis is because it always has to be negative on that interval. Otherwise, you would have another x-intercept sitting there. So that's why we can get away with saying that piece. And another component, so let's see here. I know at the y-intercept I'm above the x-axis, and I can't cross, so I have to be on this side at least up until here. Right? It might not look exactly like this, but I'm giving you a gist as to what goes down. Now, am I going to just touch that point, or am I going to cross through? Well, you can actually use multiplicities to kind of get that of the numerator. Another route, though, is you can plug in a number between that and the asymptote. So take 1.5, for example. Notice you get a plus here, minus here, and then a plus here. That makes a negative. So once we cross through that point, we're going all the way down to -infinity. Okay? And then for the last component, notice our hole occurs at a positive value. So that tells us we're going to have this graph going like this, and then we're going to get closer and closer. I'm never really touching. I know it looks like it, but and that was supposed to get close to that hole, but never actually touch it. And there's my graph. And notice I didn't touch a calculator or anything. I just used the information listed here. And that's how you can build graphs. As I said, I'm slightly off. I could check concavity of the curve. So is it concave up, meaning a cup like a parabola that's facing up, or is it concave down, meaning a parabola facing down? But for the most part, I got intervals of increasing, decreasing, as long as it isn't flatlining or anything like that. I'm pretty good to go. So hopefully that gives you an idea, and you can plug it into a calculator. Check me here and see if I'm actually accurate or not. So hopefully that makes sense on that part. If not, let me know. But all I did is just piece all those things together. So now the last couple pieces, inverses involving radicals. So we'll go through that real quick just to make sure we get the gist of that as well. So in order for an inverse to exist, we need a function to be one-to-one. And so in order for me to actually look at that, I'm going to try and draw this graph. Once again, I avoid calculators altogether pretty much, so I'm going to try and show you how to do that. It's complete the square. So you take half of this middle term, and the reason why, because we want to write, if you take half of that middle term and you square it, notice this becomes x squared minus 2x, which gives us our magical number there, and our magical beginning point. And then we go and we square the 1, so you go plus 1. But what happens is, we've added a little too much. So I can't just toss that in willy-nilly. If I've added a 1 by doing this, I have to subtract off that 1 to be at the original function. So our f of x equals something like this. Now I can take that and simplify it a bit more to be something like f of x equals, so this becomes x minus 1, the quantity squared, and then plus 3. So notice though, I'll write it one more time here, x minus 1, the quantity squared, plus 3, and hopefully you're good with your transformations of functions, because that can be useful here. So what have we done? Well, this, all we've done is shift right 1 of the graph of f of x equals x squared, and this is a shift up 3. So if we're drawing our graph, we shifted right 1, and then we go up 3 units. That's our vertex right there. And then when you plug in 0, you'll get negative, or positive 4. Sorry, I said negative. And then we go here, and then you get some curve that just, it's a parabola, goes on up and up and up and up, and up and up and up and up. Now, is this function invertible? No. It's not invertible since it is not one-to-one. Now, why is it not one-to-one? It fails. So vertical line test if it's a function. The horizontal line test if it's one-to-one. So what do? How do we fix that so we can find inverses? What we do is we restrict domain. So what I'm going to do is I'm going to create a new function. And so we can make it invertible. We'll call it f sub 1 of x. And what we'll do is we'll have the same function, but now we're going to make it one-to-one. And how do we do that? Well, we say f1 of x is x minus 1, the quantity squared plus 3, but x is now greater than or equal to 1. Simple as that. And once we can do that, if we restrict that domain, so what I've done is just basically taken this left half and got rid of it. Now I have a one-to-one function. It passes the horizontal line test. So this function is invertible. If this is f1 of x, since it is one-to-one, and it passes the horizontal line test. Okay, so that means we can take an inverse. So find inverse of this function. And that's not too bad. Here's all you do. You go same old steps that we've done before. You go y equals x minus 1, the quantity squared, plus 3. And we'll leave out that x greater than or equal to 1 because we're about to solve for x. So you get y minus 3 equals x minus 1, the quantity squared. So you take a square root, right? And so notice, when you take a square root, usually what we have to do is we have to do a plus or minus. But we can get away with that plus or minus. And the reason why is, if you look before, you have x greater than or equal to 1. And then we know that our y value is greater than or equal to 3. Right? That's important because the inverse, it switches the values of the domain and range. So now in the inverse function, the range, right, will now be x greater than or equal to 1, meaning we want the positive version here. And then the y greater than or equal to 3, or y greater than or equal to 3 will become the x greater than or equal to 3. You're just reversing the roles. That's all that happened. So this equals x minus 1. So that's why we're using the positive square root instead of the negative. So now from here, you'd add 1, square root of y minus 3 plus 1 equals x. And so then we get f inverse, or f1 inverse, I should say, of x equals the square root of x minus 3 plus 1. And notice the domain of this thing is x greater than or equal to 3. And the range, right, we can go from 0 to infinity with that. So the range is y greater than or equal to 1. And we're done. So let's see on the other side of things, rather than start with that quadratic, let's start with the root. Well, we got to find the domain and range. It kind of helps us. So the domain, notice we just need 3x minus 4 greater than or equal to 0. So that means 3x is greater than or equal to 4, and then x is greater than or equal to 4/3. And then for our range, notice we can go from 0 to infinity with that square root, and we haven't done any reflections or anything like that. So our range is y greater than or equal to, since we added 7, we've shifted up 7 units, so we just go y greater than or equal to 7. and I'll kind of explain how that works in a second. So finding the inverse, remember we set y equal to the square root of 3x minus 4 plus 7. And then we go y minus 7 equals the square root of 3x minus 4. And then moving forward from there, you get you need to square both sides to get rid of that square root. You get y minus 7, the quantity squared equals 3x minus 4. But technically what we've done when we square both sides is we've added in this extraneous root. So that's where we're going to have to come back and tie in the domain and range. Moving forward from there, though, you add 4, you get y minus 7, the quantity squared plus 4 equals 3x, and divide both sides by 3. X equals y minus 7, the quantity squared plus 4 divided by 3. And now you have what your inverse function is. F inverse of x equals x minus 7 squared, the quantity squared, plus 4 divided by 3. But notice now, you have problems in terms of if I plug in 6 for x and then 8 for x, I'm going to get the same value. That's a problem because we need it to be 1 to 1. So the fix for that is we reverse the roles. We just say our range is now our domain. So domain of f inverse of x. What was our range? Now it's going to be, in terms of x's instead of the y's, x greater than or equal to 7. And then in the second case, range of f inverse of x. You don't necessarily need to write this too often, but it's nice to know every now and then. Y is greater than or equal to 4/3. That's it, all done with that piece, and that's how you go about finding these inverse functions along with the domain. You have to restrict the domain if you're dealing with a square root. If it's a cube root, you don't have to make any restrictions. It's only even roots, so square root, 4th root, 6th root, 8th root, that's when you have to make the restrictions. Okay. So last but not least, this might look like we have to calculate the inverse. So this is usually goes in for the x in the inverse function. But if it's x in the inverse function, that means it's the y in the original function. Right? Because that's all inverses are doing, reversing roles. So that means when we look at all this thing, we just need to replace, remember f of x is the whole y, so we just need to replace that with 10. 10 equals the square root of 5x minus 8 plus 2. So now we subtract 2 from both sides. Notice we get 8 equals the square root of 5x minus 8. Square both sides, we get 64 equals 5x minus 8. Oh, here, let me write that out actually. I'll write down the 8 squared. So you get 64 equals 5x minus 8. Add 8 to both sides, you get 72 equals 5x. And notice we solve for x without even having to calculate an inverse. And that's a beautiful thing right there. So I don't see any more questions. Hopefully all this is kind of making sense and coming together a little bit more. If not, you can ask questions all the time. I'm happy to help out as much as possible. So I wish you all a good night and have a good one.